basic information about symplectic structures and symplectic geometry. Because actually symplectic geometry is a very large and well-developed branch of mathematics nowadays, with lots of problems, lots of application to various mathematical theories, to complex geometry, to algebraic geometry. In mirror symmetry, there are applications of symplectic geometry, as you know. You probably have heard. There are applications of symplectic geometry to group theory, to topology, to many, many, many other branches of mathematics. All this theory deserves to be studied. There are lots of books dealing with them. If you are interested, you can take a look at some of these books that are listed in the list of references in the lecture notes I gave you. You can ask me, I can give you some other references as well. But of course, we are not going to dive so deep into all these details, into the theory of symplectic geometry. But our purpose is much more modest. We just need to study some basic constructions from this field and prove some basic results. So last time, I gave you the definition of symplectic structure. Be a smooth manifold, not necessarily compact, but usually it is assumed to be without boundary. And symplectic form on M is any two form omega on M such that first, this form is closed, and second, this form is non-degenerate. Non-degenerate in the sense that if you choose local coordinates, then they should exist in this matrix, which I will denote by pi, or, as I explained you last time, this is equivalent to the fact that the top degree wedge product of this form with itself is non-zero. So there are a few elementary corollaries which we can derive from this definition. Now, first of all, we conclude that the dimension of M is even. Because when dimension is odd, then there cannot be symplectic non-degenerate matrices in it, right? There are no non-degenerate antisymmetric matrices on odd-dimensional vector space. Moreover, it follows immediately that M is orientable. In fact, omega raised to the top degree, which belongs to the top degree differential forms on M, is non-zero, and hence it gives you a volume form. You are used to choosing volume forms from Riemannian structure. So recall that if you have a Riemannian structure, if G is a Riemannian structure, on M, right? And you can define the volume form of M as the square root of G times dx1 wedge dxn. N is a dimension of M. Right. And the main property of this form is that it is nowhere zero. It is well defined. Defined in the sense that when you change coordinates, you obtain the same expression. And nowhere zero. It vanishes. It doesn't vanish at any point. As far as, well, of course, you can say it is positive, but actually positivity depends on the choice of orientation. So if you say that these coordinates are positive, give you positive orientation, then it is positive. If they are negative, then it's negative. So speaking about the sign makes very little sense. So this is the standard example of volume forms which you are used to, which you probably have encountered at your study of differential geometry, Riemannian geometry. So here is another example of natural volume forms, in the sense that when you take the top degree power of symplectic form, you get an element in omega 2n, sorry, of M, and it is nowhere zero. At no point. And since it is nowhere zero, you can actually say that this form defines an orientation on M. If you remember, orientation on a manifold choice of orientation amounts to the choice of nowhere vanishing top degree differential form, volume form. And also this is for any function f. You can now integrate f against the manifold by multiplying it with the top degree form. So this volume is called symplectic volume. And it is a very important part of many investigations, many studies. So also last time I gave you the definition of vector fields, of Hamilton vector fields associated with functions on M. So let me recall you this definition. If f is any smooth function on M, then you can define the the Hamiltonian field associated with f to be the raise of index operator associated with omega, or with pi, rather with pi. Let me recall you that pi is the inverse matrix of omega, applied to the covector field df, to the differential of the function f. Equivalently, which is easy to see, you can say that x of f is the unique vector field on M, such that when you apply omega to a pair x of f and y, where y is any other vector field, you obtain precisely y applied to f. For any vector field y on M. I think we checked it last time. If not, let us do it now. Have we done this? I mean, I think we have, but okay. let us write down this condition. So we don't know what xf is, but we know what is this pairing, what this pairing is. So it is just, so I'll denote xf by x, just for the sake of briefness, okay? So it is equal to yij, omega ij, sorry, times xi times yj. And this should be equal to this. What is y applied to f? That's yj df dxj, right? Just this. So now we can apply omega inverse to this. Since omega is invertible, you see that xi, so probably better to so this is some number. So this is true for all vector fields y, right? This is true for all vector fields y. So let us choose first, before I apply omega minus first, let us first choose y equal to just okay, dxj, right? Nothing else. So we see that omega I j xi, now here we have just nothing, or just one, right? And nothing else survives, is equal to df dxj for all j's. And now we can actually multiply it by pi j, probably jk on the right. And what we get is omega I j xi pi jk is equal to df dxj pi jk. Right? And we finally, here we have delta ik xi, and here we have df dxj pi jk. And up to the sign, which I promise I will never remember myself, and I probably never ask you to remember, because actually the choice of sign is totally free. You can actually choose it in any way you want. So it's probably better to put minus here. And this shows that actually this minus sign allows us to change the order of these indices and get just that xk is equal to phi kj df dxj. That's all. And that's precisely pi sharp, I believe, of df at k. Sorry. This is my, I don't know who this is. That's spam, sorry. Okay. Okay. Let's go on. So up to the sign, that's it. So that's a definition of Hamilton vector field, but for future applications, we'll need some properties of Hamilton vector fields. And I introduced some properties last time, so here they are. First of all, if you take Lie derivative in direction of a Hamilton vector field applied to omega, you get 0. So in fact, it means immediately that if you do the same trick with the symplectic volume form, you get 0 again. So symplectic volume is preserved by Hamilton flows. Well, when I say Hamilton flows, I mean flows associated with Hamilton vector fields, of course, right? It means, for instance, a simple corollary. If if M is compact symplectic manifold, and suppose we have some Riemannian structure on M. Then for every function f, we can define not only, we can define both Hamilton field associated with f and also gradient field associated with f. And I claim that gradient fields cannot be Hamilton field for any two functions, f and h. And the proof is pretty simple. If you take Hamilton function, so suppose you have a gradient field. Well, I mean non-trivial, of course. Of course, I don't assume that if they're 0, and there is no problem, of course. Okay. And here is the answer why. Proof. Any function on C infinity, sorry, on M, on compact manifold, has some top, so has maxima and minimum, has extremas. Right? And by properties of gradient vector field, almost all its trajectories, well, if a vector field is good enough, will tend to this point as the time goes to infinity, right? Because when you move along the trajectories of gradient vector field, the value of f grows. So you cannot grow indefinitely, and you can end up at some maximum, local maximum, global maximum, doesn't matter. So if you take, well, in some vicinity, in some neighborhood of this point x, which has no other extremus in its vicinity. So that's actually the condition I need. If I take some neighborhood, and this neighborhood will tend to this point as you go from t to infinity, as the t goes to infinity. The volume of this C will go to 0 as Ct, as t goes to infinity. Well, here t is denotes the flow of our vector field. On the other hand, the symplectic flow, the symplectic volume, which of course is equivalent to this, to any other, more or less all volumes are equivalent up to some constants. So symplectic volume will be constant. And that's a very nice observation. Very simple, but very nice. Okay? What other corollaries we can derive from these definitions? So one corollary I actually derived last time, was the following. Yes.
Could you repeat the explanation of why the volume tends to 0 when t tends
Because, yeah, the size of, well, t goes to just one point.
Ah, okay.
I mean, you can actually end up in any vicinity of, in any epsilon neighborhood, in any prescribed epsilon neighborhood of this point.
Okay.
Then you can estimate the volume of your Ct by the volume of this epsilon neighborhood, and it goes to 0.
Okay.
For trivial reasons.
Is that false for non-compact M?
And if M is non-compact, we are in trouble. They can, yeah, there can be no maximum. Actually.
I understand that this kind of observation
Does not apply. Yeah.
Doesn't apply,
But then there are other things here which you can still have. That's true. Sorry? Well, of course not. I mean, you take Rn, R to n. And of course, if you take some very naive function f equal to x1, say, right, with standard symplectic form here, then it's how do you call it? Its Hamilton field will be equal just to the vector field in the second direction, up to the sign. Right? And of course it is equal to the gradient of, I think, x2 with respect to the standard Euclidean form, Euclidean metric. Okay? So on non-compact manifolds you can have lots of different emergencies, lots of different phenomena. Yeah. Okay, let's go on. So last time I spoke about Poisson bracket associated with symplectic form. So if you have symplectic form omega, we can define its inverse by vector field pi, and for such pi we can define its value on two functions, okay, so covector fields associated with functions, differentials of functions, and what you get is called by definition the Poisson bracket of f and g. So you can actually rewrite it using the definition of Hamilton vector field as up to the sign again xf applied to g, right? Or the same xg applied to f, right? then it follows from the invariance of a symplectic form with regard to the action of Hamilton vector fields that the Poisson bracket verifies the Jacobi identity, which I will write down in the standard form. So it's more convenient to write it as the Leibniz rule for the bracket. So the bracket should verify Leibniz rule with respect to itself. Right. You can actually rewrite this equation in several different ways. For instance, what you have here, let's use this equation. So you have here minus xf applied to gh. What is it? It is equal to what? It is equal to, on the right, I have the bracket minus xf applied to g, comma h, minus g xf h. So if we now remove the minus, which we can do, we get another equation, which is just the same Jacobi identity, but written in a different way. Okay, that's one way you can do. You can do the same thing now twice for f and for g. So what you have here will be xf of xg of h. Observe that the minus sign has disappeared because we have used it twice. Minus, now I take this term and move it from the right to left. Minus xg xf of h. And what I have on the right will be equal to up to the sign again. I think it's minus, right? Minus x f g. I don't quite like the sign, but we need it. So what we have on the left is actually x f computed with xg, which you apply to h. And what you have on the right is just minus x f g applied to h. So since this is true for all h, we have this identity, xf xg is equal to minus x fg, if I'm not mistaken.
Simply a way to write the Jacobi identity, right?
Sorry? Yeah, it's just the same. It's just another way to write the Jacobi identity, right? Precisely. I just don't like the sign. Just let me see if the sign is correct. The sign is a little bit off. It should be plus here, but I don't know how to get rid of it.
Why do we have a minus xfg?
Oh, because we have this, right? Yeah. Why? It's a good question. I think we had it minus, right? Was it minus or plus? I don't remember. I don't remember it from the last time.
I guess it was plus.
If it was plus, it would be better, definitely. Probably, yeah. It was, yeah. I mean, I just don't remember the definition. X, f, y is equal to minus, right? Y of f, right? But that's probably what makes it plus here, right? I hope so. Please check the sign. In that case, nothing will change here, definitely, and nothing will change here, of course, right? Nothing will change here. But here I have plus. And that's better. I'm sorry. I just don't remember the sign which I used last time. These signs are not very important because you can always just change the indentation a little bit and get plus as you want. But I just wanted to be consistent with what I told you last time. So. And that played some trick with me. So here we have this identity, which is also equivalent to the Leibniz rule, actually, to the Jacobi identity. Or we can actually continue to write x sub f of g. That's also possible, right? So what corollaries can we derive from these identities? I'll concentrate on the last one. It actually means the last identity, this, which I denote with star, means it claims that Hamilton vector fields constitute a Lie subalgebra in the Lie algebra of vector fields on a symplectic manifold. Where I use the usual commutator on vector fields. Moreover,
This corollary follows from the fact
it is just the reinterpretation of this equation. So on the left, I have commutator of two Hamilton vector fields, and on the right, I have again a Hamilton vector field. So it's just.
the bracket is respected.
Yeah, on the left, I have the bracket with respect to the usual commutator. On the right, I have another Hamilton vector field. So it's a good thing to do. Moreover, the map which sends f to its Hamilton vector field is homomorphism of Lie algebras. From the Lie algebra of functions on M, which you equip with the Poisson bracket. Of course, Poisson bracket gives you the structure of Lie algebra. I hope you know what is Lie algebra, right? It's infinite dimensional here, but still it is a Lie algebra. Someone is calling me again. What's this? Володя, здравствуйте. Я сейчас на занятиях, извините, не могу. Я на лекции. Напишите. Хорошо. Ага. Всего доброго. Sorry. So we have a homomorphism of Lie algebras. From this Lie algebra to the Lie algebra of vector fields on M with bracket, with the usual commutator as the Lie bracket. Right? So this is another way to reinterpret this. We send every function to its Hamilton vector field, and then the commutator will go to the commutator. Nothing else. And probably a third thing we need to actually observe, we have to pay attention to in this situation, is that I can actually, this formula at x of f applied to g is nothing but the commutator of f and g, right? this Poisson bracket of f of g matches the theory with which I began. If you remember, I began with writing down Hamilton equations in the form P dot is equal to dH dq, which is equal to HP, right? Q dot equal to minus dH dP, which is equal to HQ. So I actually considered the Hamilton vector field associated to H.
But shouldn't the sign be divided by the
Huh?
phi dot equals minus dH over dq, and q dot is just dH over dp?
I don't remember.
The sign is not correct.
The sign is incorrect?
Mm-hmm.
Okay. You better remember better. But I'm sure about this. I'm not sure about the sign, but I'm sure about this.
We just had the seminar.
Okay. Okay. I'm sure about the right-hand side, because actually it is just the same. So as you see, in classical mechanics, we just the things we study, the objects we study, are just the Hamilton flows of functions, the flows of Hamilton vector fields. Okay, that's more or less what I told you about yesterday. Not yesterday, a week ago. Now let us speak a little bit about something new. And this something new is the important theorem which describes the local behavior of symplectic structures. So the main theorem I'm going to prove today is the so-called Darboux theorem. Damn it. Let M omega be a symplectic manifold. And let X be any point on M. Then there exists an open neighborhood U x of x in M, and a coordinate system x1, x2n in Ux such that omega in these coordinates has the standard form dx1 wedge dx2 plus dx3 wedge dx4 and so on plus dx to n minus 1 wedge dx to n. So I'm going to give you at least a sketch of the proof. And actually there are two different ways one can work in which you can move. So first the traditional proof. Let me sketch a traditional proof first. Proof traditional. I'll be a bit sketchy here because it's pretty technical but not very hard. So let f be any function on M, actually local, but not necessarily local, around X, such that the Hamilton vector field associated with f does not vanish at x. Okay, so I just pick up just to make sure.
Local around x.
I mean, local, I don't care. When I say local, I mean that I don't care about the behavior of this function, even about existence of this function outside of some small neighborhood of x.
Like locally small.
I mean, it is smooth. Probably I better say, let me consider a geom of some function in x and so on. But I mean that I don't care about the existence of this function, its behavior and everything outside of some small neighborhood of x. It can be non-existent at all. Actually, it's not the case. You can always extend your function using a partition of unity, but I don't care about it. I just care about the way it behaves at x. Okay, so let me make sure that I'm giving the right formulas. Okay. Okay. So let us consider this. Then I denote f to be p1. I mean, I'll denote this by p1, so p1, q1, p2, q2, and so on, pn, qn, in a traditional way. So you choose f to be p1 and consider the flow, the Hamilton flow of the function f of p1. So let me draw a picture. I have some point. I have the vector field which goes through this point. Okay. What else do I do? So let y be any point in M, in the neighborhood of x. Let y be any point. Then y just one thing I forgot to say. I also choose n to be some smooth surface, hypersurface, of dimension 2n minus 1, and this hypersurface transversal to the field xf. So how do you construct this surface? You just choose some coordinates in the neighborhood of this point. I choose this vector field, and you can just take the plane, the hyperplane, in the usual Euclidean sense, transversal or perpendicular to the point x, to the vector field at point x.
So simply it means that this plane plus some other plane is
This plane plus this vector field,
yeah.
xf, will give you the whole space, right? So locally you can do this. Locally you can do this. Okay, and now for every n, you can choose q1 of y to to be equal to t if g minus t or p1 of y belongs to n. So in other words, q is just the time which you need to travel from the surface n to y along the trajectory of the Hamilton vector field of P1. Just this. Then a good exercise is to show that if you take the Hamilton vector field xf and apply it to q1, you'll get precisely 1, which you can rephrase as P1 Q1 is equal to 1. And that's actually almost immediate, because t is just the time along the trajectory, right? So when you differentiate it along the vector field in the trajectory, you restore the vector field. Yeah. Okay. So now we go by induction. It's plus or minus 1 actually, but again, depending on the way you introduce the Hamilton field. Okay, now we choose M equal to the space P1 is equal to Q1 is equal to 0. So it's some hyperplane in N, as you can see, M tilde, right? Then you need to prove that restriction of omega to M tilde is symplectic. But of course, d of this restriction vanishes, right? That's clear. And then you just need to check that omega is equal to M tilde is non-degenerate. But at the point x, it is just a restriction of the matrix to the hyperplane. And there it is non-degenerate by linear algebra. So in some vicinity, it will be still non-degenerate. So you have now now you're in the situation where you can apply inductive hypothesis. You can choose coordinates P2, Q2, P3, Q3, and so on, Pn, Qn, in M tilde, right? Then you add the coordinates P1, Q1 to this set. Before that, of course, you need to extend Pi and Qi from this M tilde to the whole neighborhood. But to this end, you just consider the projection. So locally, M tilde is just some hypersurface of codimension 2 in Euclidean space. So you just choose projections along the trajectories of P1 and Q1 onto this M tilde, right? So you first project along the trajectories of P1 to N, and then you project along the trajectories of Q1 to M tilde. And then you extend, and this allows you to extend these coordinates to functions in a neighborhood of X. Right, so you need to be careful. You need to first project any point in the neighborhood to N, and then project any point in the neighborhood to M, using the trajectories of P1 and Q1. Right? And after this, you can, so locally, it's again, this system of functions will give you coordinates, and then you can check that the omega in these coordinates will have the prescribed form. So it's pretty technical, but not very hard. Observe that this does not work for a Riemannian structure. This reasoning for Riemannian structure fails precisely because, well, I think because when you choose locally orthogonal, it cannot integrate. When you choose locally orthogonal vector field, it may not integrate to a coordinate. That's not the case here.
So it works only for globally. Right?
Sorry?
For global, it works only for global.
For local, only for local.
Only for local.
Only locally. This is the local theorem. You cannot choose global Darboux coordinates. But locally, around every point, you can do this trick. So that's pretty technical, as you see. So I'll speak about another way to prove this theorem, which is based on so-called Moser's trick. So let me begin with this new part of my talk.
So can you repeat the comment on why this doesn't work in Riemannian?
Well, in Riemannian manifold, well, I think the problem, well, I never actually thought accurately about this, but as far as I can understand, in Riemannian manifold, you can obtain a set of vector fields, an orthogonal set of vector fields easily, but this orthogonal set of vector fields will not commute in the prescribed way. Here we use the fact that the pi qj is equal to delta ij, and hence all the vector fields except for pi and qj will commute. All the vector fields, actually all the vector fields, x pi, x qj, will commute. Because the Hamilton field associated with constant function is 0, right? And hence, when we obtain these vector fields, they integrate to coordinates.
Yes, by Frobenius.
Yeah, it's something on Frobenius, it's even easier than that,
Okay.
right? But if you take usual Riemannian structure, and you can again obtain such vector fields, will be orthogonal and normal in the vicinity. It's even easier than that. But then you cannot use these vector fields to integrate them to coordinates. They will not integrate to coordinates.
Frobenius theorem is about distributions.
Yeah, that's Frobenius theorem. But you don't even need it. You can deal with something simpler. It's you can derive this from Frobenius theorem. You can use this fact to prove some part of Frobenius theorem, but actually this is a simpler part of Frobenius theorem. Okay. So what I actually did, you can actually regard it like this. I constructed these vector fields locally. I can always do this locally, but it's some technical result, but you can do this. But then, since they commute, you can integrate them to coordinates, and that's it. But that's not the case in Riemann case, in Riemann situation. So let me prove the same theorem with some other trick, which is called Moser's trick. So let me begin with proving some lemma. Actually, not proving. I think I formulated. And I'll probably ask you to prove this lemma at our exercise session. Actually, it's here it is. So here is the Moser streak. Let x sub t be a time-dependent vector field on some manifold Q. Or an M, doesn't matter. Time-dependent vector field. So this is lemma, which I leave without proof. Then, if phi sub t is the flow of xt, that means that d phi t of x dt at some point t 0, right, would be equal to x t 0 of x. Is this clear? That's the definition. You can actually regard it as follows. You consider the product of x and real line, x and R1. And then consider the vector field, usual vector field, xt plus d dt. Right? You can do this. It's a usual vector field here. So you can now integrate, this is the manifold Q, sorry. So you can now integrate this vector field V along the manifold, along this product, Cartesian product, and project what you get back to X, back to Q.
When you say integrate, what do you imply?
I mean integrate, I mean consider the trajectories of this vector field. Integrate, when I say integrate, means consider the trajectories. Okay. Then here is the formula which we'll need. Then for every differential from alpha on Q, the derivative of xt, ln xt of alpha, which you pull back along this flow.
We have two manifolds or
One.
But where is it? First is M and then Q.
That's a misprint. Sorry.
Okay.
Sorry, I was going to speak about M, then I looked into my notes and there I use Q. So it's better to go from M to Q back. Okay. Would be equal to d dt phi star sub t of alpha. So this is the formula which I'm going to use. I suggest that you would prove this formula for the next time. And now I'll use this formula to prove the Darboux theorem. Actually, I prove even more than that. I prove some theorem which is called the Moser streak theorem. I'll prove two versions, and there will be a third one which I'll speak about later. Theorem Moser. Let Q be a manifold, compact and oriented. Let lambda 0, lambda 1 be two volume forms on Q. And we assume that the integral of lambda 0 along Q against Q is equal to the integral of lambda 1 against Q. Then there exists an isotopy, actually one parameter family of diffeomorphisms phi star sub t, phi t from Q to Q, such that phi 0 is equal to the identity, phi star 1 applied to lambda 1 is equal to lambda 0.
This is called isotopy.
It's called isotopy, right? Right. The proof is pretty simple. I'd even say remarkably simple compared to a traditional proof of Darboux theorem. So first of all, we observe that since the integral of lambda 0 is equal to the integral of lambda 1, it would mean that the cohomology class of lambda 0 is equal to the homology class of lambda 1. And hence, there exists beta in top minus 1 degree differential forms on Q, such that lambda 1 is equal to lambda 0 plus d beta, right? Also, for all t in real numbers, the sum, I think it's t times 1 minus t lambda, t1, t lambda 1 plus 1 minus t lambda 0 is, of course, is always top degree. But it will also be nowhere vanishing because they have the same sign, of course, right, in all coordinates, right? So when you take two, okay, let it be from 0 to 1, just to make sure, from 0 to 1. When you take two positive coefficients and multiply with some positive t and 1 minus t, you get something positive again, right, on 0. Yeah? But so here we have, so let's denote this by lambda t. So it is clear to see, it's easy to see that lambda t is equal to t times lambda 0 plus d beta plus 1 minus t lambda 0, so it will be equal just to lambda 0 plus t d beta. Okay. Now, consider for every vector field x on Q, consider the convolution, what was this? The contraction of x with lambda t. It will give you some differential form of codimension 1. And since this is non-degenerate, this convolution x goes to I x of lambda t is isomorphism between vector fields on Q and the codimension 1 differential forms on Q, right? That means that if we take beta here, then we obtain a unique a unique vector field x sub t such that ixt of lambda t plus beta is equal to 0. You can do this just by changing the sign, but that's not a problem. So what I do, I take this vector field, it's time dependent. I consider its flow phi star of t and apply it to lambda t. And then I differentiate it with respect to t. Right? Yeah. So what I get, there will be two components. First, I'll differentiate, I'll freeze t here, so to say, and I'll differentiate this part with respect to t, and then I can use the formula which I had. It will be just phi star sub t applied to the Lie derivative ln xt applied to lambda t. But then I also have d dt of lambda t. So phi star of t will go outside, but when I differentiate lambda t ln t, I'll get just d beta, right? Now, this, by Cartan's magic formula, is equal to d y ixt plus ixt d. The second part vanishes because lambda t is top degree, so its differential is equal to 0. And what we have will be equal to phi star t d y ixt of lambda t plus beta. And that's 0. Right? So it means that it is constant. And it will be equal to lambda 0 and t is equal to 1. T is equal to 0. And so phi 1 verifies this condition. Very nice theorem. Now you can use the same trick, precisely the same trick, for symplectic forms. Very nice trick effect. Theorem. Let omega. So I'm going to prove the Darboux theorem using this trick. I begin with the following observation. So we have two omega 0 and omega 1, two differential forms, two forms. On Q, I can be on Q. Two symplectic forms. Okay. Let us assume that omega 1 even worse than that. Sorry. Just don't want to do some double job. Yeah, probably better to begin with something simpler. So begin with omega t at once. So I'll repeat the same a bit later. So this would be a family of symplectic forms, and assume that omega t is equal to omega 0 plus t d beta. Then there exists an isotopy again, phi t, such that phi star t of omega t is equal to omega 0. The proof is precisely the same. Just instead of taking I sub x as the isomorphism from differential top forms I sub x of lambda. So we considered I sub x of lambda as an isomorphism between differential top forms. Differential of the vector fields on Q with differential top minus 1 form. Yeah, we used to do this. Now we consider the same map applied to omega sub t. Here we used omega lambda. And it will give us, because this is symplectic, an isomorphism between vector fields on Q and differential 1 forms on Q. Right? Again, the same trick. After this, I think it's not even necessary to have t here. You can just put beta sub t. After this, you just take the equation I sub xt of omega t is equal to plus dt of beta t is equal to 0. And this gives you a unique vector field xt, which verifies this condition. And then you consider the flow of this vector field again. And if you apply it to omega sub t and differentiate it with respect to t, then you get precisely the same equation. First, you'll get phi star xt applied to L xt, the lead derivative with respect to xt, applied to omega t, plus plus d dt applied to omega t. So in the first case, you use again the Cartan's magic formula, d ixt plus ixt d. So the second term vanishes because it is closed, because it's symplectic. And here, you differentiate this equation, this term vanishes, and here you'll get d of d beta dt. So eventually you'll get phi star x sub t d of ixt of omega t plus d beta dt. And that's 0 again by this equation. Nice. So you see, this works perfectly well. And now we finally apply it to Darboux theorem. You can now call it Darboux-Moser theorem. So for every point x in M exists an open neighborhood of this point in M, and coordinates P1, Q1, Qn such that omega in these coordinates will be equal to P1 dP1 which dQ1 and so on plus dPn which dQn. A proof is a magic thing to do. It's magically simple. You take some point. So first of all, you can consider M equal to some open neighborhood of the origin in R to N. You can assume it just by choosing. So since you work only locally, you can assume this. Since need only local situation. So let omega be the given non-standard symplectic form on R to N. And let omega 0 be the standard differential form, this one, on R to N. Without loss of generality, we can assume that when you restrict omega to the origin, you get precisely the standard form at this origin. You can do this by linear change of coordinates. It's not a problem at all. So now consider omega t equal to t omega plus 1 minus t omega 0. Omega t at the origin is symplectic, since it's always equal to omega 0 at this point. Hence there exists an open neighborhood of the origin where omega t will be symplectic. For all t from 0 to 1. That's possible because the segment is compact, right? Okay, further. Since both forms are closed, and we work in an open neighborhood of the origin in Euclidean space, being closed means that they're exact. So we can actually write down omega equal to omega 0 plus d beta, and hence omega t will be equal to omega 0 plus t d beta. So we are now in the situation described by the previous lemma, by the previous theorem. We have a family of symplectic forms, omega t, a family of one forms beta t equal to t beta, right? such that omega t is equal to omega 0 plus d beta t. And by the previous construction, we can find phi t such that phi star t of omega t is equal to omega 0. And hence, in particular, the phi star of 1 of omega will be equal to omega 0. And that's precisely the coordinate change we need. As you see, it's remarkably simple, just one-liner. And moreover, the same trick allows you to prove a relative Darboux theorem. So suppose you have, I am not going to formulate it, even less I'm going to prove it. Just imagine that you have some symplectic manifold, and inside this symplectic manifold you have some submanifold with prescribed symplectic form on it. So suppose you have some submanifold K in M, and suppose you have a symplectic form omega, two symplectic forms, omega on M, omega 0 and omega 1 on M. And suppose that omega 0, when you restrict it to K, is equal to omega 1 when restricted to K. And I suppose that K is compact, of course. Otherwise, I'll be in trouble. Then there exists an open neighborhood of K, and a diffeomorphism, I believe, of this neighborhood of phi u to u, such that phi is identical on K and phi star of omega 1 is equal to omega 0. As far as I can remember, is this. That's sometimes called relative Darboux theorem. Here, K, in our case, K was equal to the point. Omega 0 was the standard symplectic form. And omega 1 was, the usual omega 1 was the given symplectic form. So that's all. So how much time do I still have? Sorry, no time. Yeah, precisely. So that means that it is good time to stop, because next time I'll speak about Poisson structures, which are generalizations of symplectic structures. And my purpose would be to introduce all the geometric structures we need to speak about deformation quantization. So I'll do this, I think, in a couple of lectures. Okay, thank you.